Well, as much as I hate to be the bearer of bad news, as much as I hate to break it to you, it's that time again. It's that time where we are doing the math in this very era. Now, in this part of the video, we are going to be diving into exponential functions. Now, I'm going at it with the presumption that you've joined us in from the beginning of our video series where we introduced functions and got our creative and intuitive and otherwise juices flowing, right? So in here, I'm just gonna try and move at the snail's pace while trying my very best not to regurgitate the same stuff over and over again. Right. So training wheels on, strap up, get your notepads out, and just pay attention. I will break down exponential functions for you. Now, seeing as that we are saying in here, we are dealing with an exponential functions. It means some of what we know from exponential expressions, exponential laws, exponential equations will come in very, very handy in solving or working out functions, right? So the story hasn't changed. The story still dials back to what you and I already know at this point in time from our introduction to functions. And this is the short version of the story, is that functions is nothing but a study of relationships. Now, these relationships are the relationship between X and Y. Simple as that. The relationship between the input and the output. Remember the story? Simple as that. In every function, there's gonna be something in between, the rule. Now, in this point in time, the rule is no longer y is equals to mx plus c, but the rule has now transitioned into something quite yet different. Now, this rule of ours, that's what we would name our standard form. Like I said in linear functions, that everything starts with our standard form. In exponential functions, this in here would be our standard form. Now, in this standard form of ours, we are going to be assuming for this part of the video series, with the exception of inverse functions, we are going to be going at it with the assumption that our a is equals to 1, essentially, right? Outside the scope of exponential functions, our b is gonna be either greater than 1, as we have in this scenario, first scenario in here, when b is greater than 1. Our graph is gonna be increasing from left to right. As we go from the left hand side to the right hand side, our graph is going to be increasing like so when our b is greater than 1. Bear in mind that in the first scenario, b is definitely positive from 1 and above, anything above 1, right? Now, coming into the second scenario in here, b is still positive. In the second scenario, b is greater than 0, but less than 1, meaning between 0 and 1, right? b is still positive in this scenario. So like I said, we are going at it with a presumption for this part. Unless I state otherwise, we are still going at it with the assumption that our a is 1 and our b is going to be between either greater than 1, as in the first scenario, or it's going to be between 0 and 1, as in the second scenario. Now, when our b is between 0 and 1, like so, our graph is gonna then be decreasing from our left-hand side all the way going to our right-hand side, like so, right? So now these two sketches tell you a simple story. They tell you the story of B from our standard form, right? The X is still the X, the input. The Y is still the Y. Not the Y for the question why, but the Y for the output in relationship to the input, which is the X that we studied in our spider web. Like I said, the spider web, the simple story, remember the simple spider web, you've got the grip of functions, you've got the first step right. What about our A? We are still going at it with the assumption that our A is positive 1. Simple, right? These two scenarios are assuming that our A is positive 1. Right. Now, you may be wondering, now, sir, what of that P and that Q? What do those things mean? What are they saying? I need to understand what those mean, right? So, this graph of exponents or the exponential function has an asymptote. Now this asymptote is delineated by this Q of ours. It represents the asymptote. What is an asymptote? It's that asymptote, pardon my spelling there, my spelling is not so okay right in there, but yeah, the idea is the asymptote is that imaginary line that we use when, or we respect when the graph approaches the line. It doesn't ever at any given point in time touch the line. However, it does make an attempt to approach the line. Now, this asymptote of ours is always going to be horizontal, so to speak. Horizontal, meaning parallel to the x-axis. Every asymptote that we are going to have for the part of exponential functions outside the scope of inverse functions is gonna be having a horizontal asymptote. I'm saying that slow so that it sticks in, right? Now, that's the first part about our Q. What's the second part about our Q? Is that this Q represents a shift. Now, the shift could be either in the graph being shifted in the upward direction from a certain point, or the graph could be being shifted in the downward direction from a certain point. Now, when we are shifting in the downward direction, we say we minus Q units. If we want to shift the graph down 2 units, that is to say we would minus 2 units. If we want to shift the graph upward, we add Q units. That is to say, if we want to shift the graph up 3 units, we would add 3 units to the equation of that given particular graph, right? So our Q then denotes 1, a shift. Second, it tells us where our asymptote is. It tells us where that imaginary line that is parallel to the x-axis is on the graph. It tells us where that imaginary line cuts the y-axis. That's what our Q tells us. That's the two things it tells us. And then what then of our P? This P tells us a shift as well. But the shift is not up and down. You can see that the P is very close to the X, hey? the x is going left and right, the x is going left and right. So like the x, the p, seeing as the p is very close to the x in this standard form of ours with regards to exponential functions, the p is also a left and right shift. But, I'm saying buts many times for a specific reason. When you are dealing with a horizontal shift, meaning shifting left and right, dealing with the P. When you are shifting to the left, meaning when you are shifting to the negative x-axis, we add P units. I hear myself. When you are shifting to the left of us, our x's are negative. X is positive this side. Same applies here. X is positive. X is negative this side. So when we are moving to the left, we are moving towards a direction where the x-axis is negative. When we are moving to that position where the x-axis is negative, when we are moving in that direction where the x-axis is negative, we add p units. So it has that opposing effect. When we are moving to the negative part of x-axis, we add p units in order for us to move left. By the opposing effect, when we are moving to the right of our Cartesian plane, when we are moving to the right hand part where the x is positive, we subtract p units from that standard equation. So the p represents a shift, the q represents a shift, but not just a shift, and also an asymptote. Right, what's an asymptote? It's that imaginary line that the graph approaches but never cuts. So that's it about the first part of introducing us to linear functions. So just to do a quick recap, the story still remains the same. Functions is nothing short of a study of relationship between what? One party and the next party. The first party being the input, ergo the x values, the domain. Second party being the output, ergo y values, ergo the range. Between the domain and the range, there's always the rule. When dealing with exponential functions, this is our standard form. On the right hand side of the equal sign, that's our rule right there. That's our output is equals to the rule. Thank you very much. Join us for the next video part of our video series, where I will be diving now into the next conceptual matters as specifically relates into exponential functions. Therein, from that point in time, I will be going into now the sketching of an exponential functions, giving you the steps or the breakdown strategies as to how to approach these exponential functions going into the future. And please, if you are looking for an ongoing tutoring basis, look no further. Our website is in the description. Check it out. See you in the next side.